Hey everyone, and welcome to the penultimate video in our series on D-block chemistry. And this time we're going to look at a couple of special cases, some that are quite different to what we've looked at with the octahedral and tetrahedral geometries. So they're a bit different, and they deserve a video in their own right. And they're both actually derived from octahedral geometries, which is nice. And these are namely the square planar geometry and some Yantella distortions. So first up, let's look at square planar complexes. I touched on them briefly in the video on coordination numbers and geometries last lecture, but we'll have a look at the actual crystal field splitting patterns and that now. So it's possible, but very hard, to derive the splitting pattern from the point charge model and the orbital interactions we used, like we did for the octahedral and tetrahedral ones, where we looked at each of the 5 d orbitals and how the point charges come towards them. It is possible to work out the splitting pattern that way, but it's quite hard. So it's much easier to start with an octahedral splitting pattern, which is what I'm going to demonstrate in this nice open space down here. So and the reason actually for this, before I start, is that you can see that a square planar is actually just an octahedral complex with the two what are called transligands, these that have like the z-axis component removed, and then you've just got the square planar in the middle. So if we start with the normal octahedral splitting pattern, we've got the EG and T2G orbitals, and it's actually important this time to remember the D labels for each of these orbitals as well. So these were the DXY, DYZ and DXZ orbitals, and then at the top was the dx squared minus y squared and the dz squared orbital. And this is very important because we're starting with the octahedral pattern, and as it shows here, removing the ligands from the x-axis. So what this means is that any d orbital that has a z component is actually stabilized. So what happens then is that we can change these slightly. So these T2G orbitals, we can see that there are 2 with a z component, so the dyz and dxz. These are stabilized, so they go to a lower energy, dyz, dxz, and this dxy therefore has to go to a higher energy to make up for that. Let's make it slightly higher than that, because obviously the sum, it can't gain or lose energy or anything. The total energy of the orbitals has to stay the same. So the one without a z component isn't stabilized, therefore it's destabilized, and the dxy ends up in there. And then we can do exactly the same thing for the EG orbitals here. So the dz squared gets stabilized, and it can actually go below the dxy, and then likewise the dx squared minus y squared gets destabilized and ends up all the way up here. So I've got a note here with the star. This is super important to know. The actual order of the orbitals does depend on the metal and the ligands. So I've drawn it this way, and this is quite a common way to draw the crystal field splitting pattern for a square planar complex. However, these two certainly can be the other way around, but so it's important to know that it can change, but what's always certain is that there's a large gap between the dx squared minus y squared and whatever is the next highest in energy. So essentially, start with the octahedral splitting pattern. Because we've removed any z ligands, anything with a z component gets stabilized, anything without a z component gets destabilized to make up for it, and so that the energies all still add up to 0. So we can't actually calculate, like we could with the octahedral and tetrahedral, whether a square planar is more stable, but we can look at certain things that give us an indication that square planar will happen. So it only occurs with a very high crystal field stabilization energy. And this is because the crystal field stabilization energy has to make up for the loss of electrostatic forces from those two Z ligands being taken away. So we need a high value of crystal field stabilization energy. So things that contribute to a high delta O will help contribute to a higher crystal field stabilization energy. So for example, high ligands, strong field ligands in the spectrochemical series, so things high up here, like the cyanide anion. So for example, nickel tetracyanate is square planar. So this because it's got a strong field ligand. Also, second and third row metals, we said before, they give a very large value of delta O. So therefore they can give us a very high crystal field stabilization energy. So things like platinum tetrachloride, that's also square planar. And this is actually the basis for a lot of the anti-cancer drugs I showed on I think the very first video of the series on D-block metals. So if you go back and look at them, there is a cisplatin and carboplatin. They're all square planar platinum complexes. So second and third row metals they're much more common for, and they're generally only observed for D8 and D9 electronic configurations. Now, Yantella distortions are another thing that can happen to octahedral complexes. And let's take a sort of case study to show what they are and why they occur. So if we're looking at copper hexa aqua 2+ ion, this has octahedral geometry, but if you measure the Cu oxygen bond lengths, they're not all the same. So all of these on what would be the square planar unit, say, are 197 picometers, but these axial ones along the z-axis are measured to be 226 picometers. And this is called a tetragonal distortion. So whenever we've got either an elongation or a shortening of the bonds along this z-axis, that's called a tetragonal distortion. It's important to know from the off that the Yantella effect doesn't actually predict whether they will elongate or shorten, just that there will be a distortion along this z-axis. Now the reason for this is that with the electronic configuration of copper 2+, it's D9, but there are actually two possible ways of doing it. And both are degenerate at the moment anyway. So it's D9. We can either, it will have 3 Eg electrons, but either they can both be in the dz² orbital, or the pair of them can be in the dx² minus y², and then the single one is on the opposite one. And whenever we see a complex that has a degenerate ground state, like what we just saw with the copper D9, where it can have one of two Eg occupations, a Yantella effect can occur. So this is because of distortion causing one of the orbitals to have a lower energy than the others. An occupation of this orbital causes a lower overall energy for the structure. So in the example we saw, which is here, it was the z-axis, or the z component, was elongated, and that caused anything with a z component of the orbitals to be stabilized, whereas those without a z component are destabilized. Quite similar to what we saw with the square planar. In fact, it's just the z-axis ligands still exist, so it's not quite so dramatic. But here we see what happens. So these two again, xz and yz, get stabilized, whereas xy is slightly destabilized, and dz² is stabilized, and dx² minus y² is destabilized. Now, it's not a massive change, but it means that there is a configuration that causes a lower overall energy, and that's why we get this elongation along the z-axis, is to cause this lower overall energy rather than having the degeneration. And as I said, Yantella distortions can occur whenever there's a degenerate ground state. So if we look at D4, in particular the high spin D4 electronic configuration, I'll draw it out here, but this is also a time that it can occur. So 1, 2, 3, 4. This lonely electron in the Eg orbitals could be in here, or it could be in this one. So again, we've got this uneven occupation of Eg orbitals. And the reason the effect is so large, especially in these octahedral complexes, is because the dx² minus y² and dz squared orbitals have different shapes, but they're all directed directly at where the ligands are coming from. So you can imagine if there's a distortion in the z direction, so these z bonds are elongated as we've seen, there's less electron-electron repulsion along in this dz squared orbital. So this one becomes slightly lower in energy compared to the x squared minus y squared, which has the shorter bonds and again ligands coming directly at it. So that's why a distortion in this, like this tetragonal distortion along the z-axis, makes all of the z component orbitals slightly lower in energy, and that's why we get this distortion. Now the reason it's not so pronounced in tetrahedral complexes, or kind of why we really focus on octahedral complexes with the Yantella distortion, is because I said it's possible whenever there's a degenerate ground state, so it's possible in tetrahedral complexes too. However, when we looked at the crystal field splitting pattern for tetrahedral, we noticed how none of the ligands are directed directly at any of the z orbitals, d orbitals, sorry. So therefore, even though there is a Yantella effect, it's not a very strong one, and you can't really see it as well as you do for these octahedral complexes. Another example is even with octahedral complexes, it's possible with other deconfigurations. So like if we look at D1 or D2, they will again have either 1 or 2 electrons in the T2G orbitals. But so you can imagine it could either be these two or this one and this one. Like it's a degenerate ground state again. But these T2G orbitals don't actually point directly at any of the have a ligand pointed directly at them. So therefore the distortions are too small to measure, and they kind of get neglected. So that's why D4 and D9 octahedral complexes are the ones you really need to know for the Yantella distortion, because they'll have this elongated Z component.